Hello, dear students, welcome to massive open online course on Swayam in chemistry. Myself Preeti Kiran, PGT Chemistry from Kendriya Vidyalaya No. 1, Air Force Station, Hindon. Dear students, in the previous module, you have studied about how to derive integrated rate equation for the zero and the first order reactions. And also we studied the determine the rate constant for zero and the first order reactions. And we also determined the half-life of a reaction. Today we will study about the temperature dependence of the rate of a reaction, that is Arrhenius equation. And we will study about the effect of catalyst and the collision theory of chemical reactions. So let's discuss each. The first one is the temperature dependence of the rate of a reaction. For most of the chemical reactions are accelerated by increase in temperature. That is, the rates of the reactions increase with the increase in temperature. For example, in decomposition of N2O5, the time taken for half of the original amount of the material to decompose is 12 minutes at 50 degrees Celsius. It takes 5 hours at 25 degrees Celsius and 10 days at 0 degrees Celsius. Also in a mixture of potassium permanganate, that is KMnO4 and oxalic acid H2C2O4, potassium permanganate gets decolorized faster at a higher temperature than at a lower temperature. It has been found that for most of the chemical reactions with rise in the temperature by 10 degrees Celsius, the rate constant is nearly doubled. The temperature dependence of the rate of a chemical reaction can be accurately explained by Arrhenius equation. It was first proposed by Dutch chemist J. H. Van't Hoff, but Swedish chemist Arrhenius provided its physical justification and interpretation. The equation is K is equals to A exponential factor raised to power minus EA upon RT, where A is the Arrhenius factor or the frequency factor. It is also called pre-exponential factor. It is a constant specific to a particular reaction. R is a gas constant and EA is activation energy measured in joules per mole. A reaction can occur when the reactant molecules colloid with each other and form an unstable intermediate with higher energy. The lifespan of the unstable intermediate is very short and thus it leads to the formation of a stable product. The energy required to form this unstable intermediate, also known as an activated complex, is known as the activation energy. It is in the form of a symbol written as capital E with subscript small a. Here you have the energy profile diagram, and from the graph you can see the average energy of the reactants and products, and also you can see the activated complex and the activation energy. It just illustrates the activation energy involved in a reaction. It can be understood clearly using the following simple example or a simple reaction. 1 mole of hydrogen reacts with 1 mole of iodine to give 2 moles of hydrogen iodide. According to the Arrhenius, this reaction can take place only when a molecule of hydrogen and a molecule of iodine colloid to form an unstable intermediate. It exists for a very short time and then it breaks up to form 2 molecules of hydrogen iodide. Figure shows you the formation of the intermediate. The formation of the hydrogen iodide through the intermediate. As discussed earlier, the energy required to form this intermediate is known as activation energy EA. It is obtained by plotting potential energy versus reaction coordinate for this reaction. The reaction coordinate represents the profile of energy change when reactants change into products. Initially, the energy increases as the breaking of the bonds of HH predominated. After reaching maxima, due to the dominance of the process of the bond formation, energy is released resulting in the formation of the products. So, the final enthalpy of the reaction depends upon the nature of the reactants and products. All the molecules in the reacting species do not have the same kinetic energy. Since it is difficult to predict the behavior of any one molecule with precision, Ludwig Boltzmann and James Clerk Maxwell used statistics to predict the behavior of large number of molecules. According to them, the distribution of the kinetic energy may be described by plotting the fraction of the molecules, that is Ne upon Nt, with a given kinetic energy capital E versus kinetic energy. Here Ne is the number of the molecules with energy E and Nt is total number of the molecules. Here again you can see the distribution curve showing energies among gaseous molecules. The peak of the curve corresponds to the most probable kinetic energy, that is kinetic energy of maximum fraction of molecules. There are decreasing number of molecules with energies higher or lower than this value. Also, it has to be noted that only those collisions result in the formation of the products whose energies are equal to or more than the threshold energy. Threshold energy is the certain minimum energy required for forming the products. Hence, the activation energy can be defined as the energy required to cross this barrier between the reactants and the products and is given by the kinetic energy of the molecules. Activation energy is equals to threshold energy minus average energy of the reactants. EA is equals to ET minus ER. The activation energy depicts the fraction of effective collisions, that is small f, and thus possess a definite value for a particular reaction. For a given reaction, if activation energy is low, then the number of the effective collisions is large, resulting in higher rate of reaction. On the other hand, for the reaction with higher activation energy, the number of the effective collisions is low. Hence, such reactions proceed with a lower rate. Now, again you can see a distribution curve showing temperature dependence of rate of reaction. When the temperature is raised, the maximum of the curve moves to the higher energy value, where the curve broadens out, that is spreads to the right, such that there are greater proportion of the molecules with much higher energies. The area under the curve must be constant, since total probability must be 1 at all time. We can mark the position of EA on Maxwell-Boltzmann distribution curve. Increasing the temperature of the substance increases the fraction of the molecules which colloid with energies greater than activation energy. It is clear from the diagram that in the curve at T plus 10 degrees Celsius, the area showing the fraction of the molecules having energy equal to or greater than activation energy gets doubled, leading to a doubling the rate of reaction. In the Arrhenius equation, the factor exponential minus EA by RT corresponds to the fraction of the molecules that have kinetic energy greater than activation energy. Taking natural logarithm of both sides of the equation 1, we get natural logarithm k, that is ln k, it is a natural logarithm. K is equals to minus EA by RT plus natural logarithm of A. The plot of ln k versus 1 by t gives a straight line according to the equation 2. You can see in the figure. Figure shows you the plot between natural logarithm k and 1 by t. Thus, it has been found from Arrhenius equation that increasing the temperature or decreasing the activation energy will result in an increase in the rate of the reaction, and an exponential increase in the rate constant. Slope is equals to minus EA by R and intercept is equals to ln A. So, we can calculate activation energy and capital A, that is pre-exponential factor, using these values. At temperature T1, equation 2 will become ln K1 equals to minus EA by RT1 plus ln A. This is now equation number 3. Now, the next equation at temperature T2, equation 2 will become ln K2 equals to minus EA divided by RT2 plus ln A. Now, this is equation 4. Since A is constant for a given reaction and where K1 and K2 are the values of the rate constants at temperature T1 and T2 respectively. Now, subtracting equation 3 from equation 4, we obtain ln K2 minus ln K1. Ln, I am saying it is natural logarithm. So, ln K2 minus ln K1 is equals to minus EA by R T2 minus EA by RT1. It come out to be EA by RT1 minus EA by RT2. Now, the expression will become ln K2 by K1 is equals to EA by R 1 by T1 minus 1 by T2. Now, taking the log, that is at base 10, log is equals to K2 by K1 equals to EA by 2.303 R 1 by T1 minus 1 by T2. Log K2 by K1 is equals to EA by 2.303 R T2 minus T1 upon T1 into T2. So, now this is the expression which we will frequently use in the numericals. Here, where there are two temperatures T1 and T2, and then there are two rate constants. At temperature T1 it is K1 and at temperature T2 the rate constant is K2. R is the universal gas constant and EA is activation energy. Now, this is the expression, children, which you are using different numericals. I am taking numerical number 1. The rate constant of a reaction at 500 Kelvin and 700 Kelvin are 0.02 per second and 0.07 per second respectively. Calculate the values of EA, that is activation energy, and capital A, that is Arrhenius factor. It is a simple numerical based on the expression. Now, we know that log K2 by K1 is equals to EA by 2.303 upon R T2 minus T1 divided by T1 into T2. Now, just putting up the values, K1 it is 0.02 per second given, K2 is equals to 0.07 per second, T1 is equals to 500 Kelvin and T2 is equals to 700 Kelvin. And let me tell you here that if the temperature is given in degree Celsius, then you have to change the values in Kelvin before putting them in the formula. Capital R is a gas constant, 8.314 joules per Kelvin per mole. Now, putting the correct values in the formula, it becomes log 0.07 divided by 0.02 equals to EA divided by 2.303 into 8.314 and then 700 minus 500 divided by 500 into 700. Finding out the log, it comes out to be 0.544 equals to EA into 5.714 into 10 raised to power minus 4 divided by 19.15. Activation energy EA is equals to 0.544 into 19.15 divided by 5.714 into 10 raised to power minus 4. Calculating it, it comes out to be 18230.8 joules. Since K is equals to A exponential minus EA by RT, putting the values 0.02 equals to A exponential minus 18230.8 divided by 8.314 into 500. A is equals to 0.02 divided by 0.012. It comes out to be 1.61. I am taking another numerical problem based on the same Arrhenius equation. The first order rate constant for the decomposition of ethyl iodide by the reaction C2H5 in the gaseous state gives ethene C2H4 plus hydrogen iodide in the gaseous state at 600 Kelvin is 1.60 into 10 raised to power minus 5 per second. Its energy of activation is 209 kilojoules per mole. Calculate the rate constant of the reaction at 700 Kelvin. Now let's solve it. We know that log K2 minus log K1 is equals to EA divided by 2.303 R 1 by T1 minus 1 by T2. Log K2 equals to log K1 plus EA by 2.303 R 1 by T1 minus 1 by T2. Now the given data is K1 is equals to 1.60 into 10 raised to power minus 5 per second. Activation energy is given 209 kilojoules per mole. Now it is given in kilojoules, so we have to convert it into joules. So it will become 209,000 joules per mole. Temperature T1 given in Kelvin 600 Kelvin and T2 is 700 Kelvin. Now putting up the data in the given formula, let's see what happens. Log K2 is equals to log 1.60 into 10 raised to power minus 5 plus 209 into 10 raised to power 3 divided by 2.303 into 8.314 into 1 by 600 minus 1 by 700. Log K2 is equals to minus 4.796 plus 2.599. It comes out to be minus 2.197. So finding the anti-log, the K2 will be 6.36 into 10 raised to power minus 3 per second. Another example, the decomposition of the hydrocarbon follows the equation. K is equals to 4.5 into 10 raised to power 11 per second E, that is exponent, minus 28000 K by T. Calculate activation energy. Now according to the Arrhenius equation, we have the expression K is equals to A exponent minus EA by RT. On comparing the equation to the given equation, we get minus EA by RT is equals to minus 28000 K by T, or EA by R is equals to 28000 K. Hence EA is equals to 28000 K into R. It is equals to 2800 K into 8.314 joules per Kelvin per mole. After calculating, the value is 232792 joules per mole. In kilojoules, the answer will be 232.79 kilojoules per mole. Now I am going to discuss one more example. The activation energy for the reaction 2 moles of hydrogen iodide gives 1 mole of hydrogen and 1 mole of iodine is 209.5 kilojoules per mole at 581 Kelvin. Calculate the fraction of the molecules of the reactants having energy equal to or greater than activation energy. Now let me solve this. In the dissociation reaction of hydrogen iodide, given is activation energy EA is equals to 209.5 kilojoules per mole. Now change it into joules, it becomes 209,500 joules per mole, temperature 581 Kelvin and R is equals to 8.314 joules per Kelvin per mole. Now let the fraction of the molecules of the reactants having energy equal to or greater than the activation energy be X, and then we have X is equals to E raised to power minus EA by RT. ln X is equals to minus EA by RT, or log X is equals to minus EA by 2.303 RT. Now just putting the values, log x is equals to minus 209500 divided by 2.303 into 8.314 into 581. After calculation, the value comes out to be minus 18.8323. X is equals to NT log of minus 18.8323. The answer comes out to be 1.47 into 10 raised to power minus 19. So just now we have done many numericals based on the Arrhenius equation. Now let us discuss about the effect of the catalyst. A catalyst is a substance which increases the rate of a reaction without itself undergoing any permanent chemical change. In other words, a catalyst is one which provides an alternate pathway or the mechanism of lower activation energy to form activated complex readily. It gets involved in the reaction chemically but temporarily and continually changes as reaction proceeds. For example, MnO2 catalyzes the following reaction so as to increase its rate considerably. Reaction is 2 KClO3 gives 2 KCl plus 3 O2. This reaction is catalyzed by MnO2. The word catalyst should not be used. When the added substance reduces the rate of the reaction, the substance is then called inhibitor. The action of the catalyst can be explained by intermediate complex theory. According to this theory, a catalyst participates in a chemical reaction by forming a temporary bonds with the reactants, resulting in an intermediate complex. This has a transitory existence and decomposes to yield products and the catalyst. As mentioned above, it is believed that the catalyst provides an alternate pathway or the reaction mechanism by reducing the activation energy between the reactants and the products, hence lowering the potential energy barrier. Here in the graph now you can see the potential energy barrier and the impact of the catalyst. The effect of the catalyst on the activation energy is that it has lowered the activation energy. It is clear from the Arrhenius equation that lower the value of the activation energy caused by the catalyst, higher will be the rate of reaction. For example, in ozone cycle, the depletion of ozone to oxygen speeds up in the presence of chlorine. Chlorine breaks down the ozone molecule to form a little stable intermediate chlorine oxide ClO, which readily decomposes to oxygen molecule and chlorine. Here you can see again the graph and the effect of catalyst chlorine on the depletion of ozone. A small amount of catalyst can catalyze a large amount of reactants. A catalyst does not alter Gibbs energy. Delta G of a reaction, it catalyzes the spontaneous reaction but does not catalyze non-spontaneous reactions. It is also found that a catalyst does not change the equilibrium constant of a reaction, rather it helps in attaining the equilibrium faster. That is, it catalyzes the forward as well as backward reaction to the same extent, so that the equilibrium state remains same but is reached earlier. Now let us discuss about the collision theory of chemical reactions. Though Arrhenius equation is applicable under a wide range of circumstances, collision theory, which was developed by Max Strauss and William Lewis in 1916 and 18, it provides a greater insight into the energetic and mechanistic aspects of the reactions. It is based on kinetic theory of gases. According to this theory, the reactant molecules are assumed to be hard spheres and the reaction is postulated to occur when the molecules colloid with each other. The number of the collisions per second per unit volume of the reaction mixture is known as collision frequency, represented by capital Z. Another factor which affects the rate of a chemical reaction is activation energy, as we have already studied for a bimolecular elementary reaction. Let's take an example, A plus B giving products. The rate of a reaction can be expressed as rate is equals to capital Z subscript AB exponent raised to power minus EA by RT, where ZAB represents the collision frequency of the reactants A and B, and exponential raised to power minus EA by RT represents the fraction of the molecules with energies equal to or greater than activation energy. Comparing equation 6 with Arrhenius equation, we can say that A, that is the Arrhenius factor, is related to collision frequency. Equation 6 predicts the value of the rate constants fairly accurately for the reactions that involve atomic species or simple molecules, but for complex molecules, significant deviations are observed. The reason could be that all collisions do not lead to the formation of the products. The collision in which molecules colloid with sufficient kinetic energy, called threshold energy, which is the sum of activation energy and energy possessed by reacting species, and proper orientation, so as to facilitate breaking of bonds between the reacting species and the formation of the new bonds to form the products, are called effective collisions. For example, formation of methanol from bromoethane depends upon the orientation of the reactant molecules as shown in the figure. The proper orientation of the reactant molecules lead to bond formation, whereas improper orientation makes them simply bounce back and no products are formed. Here in the figure you can see the impact of the collision and the effect of the proper orientation. If the molecules are properly oriented, products are formed, and if they are not properly oriented, no products are formed. The diagram shows you the molecules having proper and improper orientation. To account for the effective collisions, another factor P, called the probability or the steric factor, is introduced. It takes into account the fact that in a collision, molecules must be properly oriented. So now the expression is rate is equals to P into ZAB exponent raised to power minus EA by RT. Thus, in collision theory, activation energy and the proper orientation of the molecules together determine the criteria for an effective collision and hence the rate of a chemical reaction. Collision theory also has certain drawbacks, as it considers atoms or molecules to be hard spheres and it ignores their structural aspect. You will study details about this theory and more on other theories in your higher classes. Now, I am just taking another example to explain the concept. In certain reactions, large fraction of molecules possess more energy than the threshold energy. Still, the reactions proceed with slow rate. Explain. The solution is, according to the collision theory of chemical reactions, a collision will be an effective one when the particles possess minimum activation energy and a correct alignment. In this case, the particle possesses more energy than the threshold energy, but still the reaction is slow. The reason is the collisions are not taking place in proper orientation. So now let me summarize what we have studied in this module. In this module, we have learnt about the effect of temperature and the catalyst on the rate of a reaction. Temperature dependence of the rate constant is described by Arrhenius equation. K is equals to A E minus EA by RT, or ln K is equals to minus EA by RT plus ln A EA, corresponds to the activation energy and is given by the energy difference between activated complex and the reactant molecules. and A, that is the Arrhenius factor or the pre-exponential factor that corresponds to the collision frequency. The equation clearly shows that the increase of temperature or lowering of activation energy will lead to an increase in the rate of a reaction. This increase in the reaction rate due to rise in temperature is in consequence of the increased number of effective collisions per unit time with temperature. Catalyst is a substance which provides an alternate pathway for the formation of the product readily and thus increases the rate of a reaction. A catalyst actually lowers the activation energy by providing an alternate path for the reaction. Catalysts are chemically involved in the reaction mechanism but get regenerated before the completion of the reaction. We have learned in this module that a reaction occurs due to collisions. This defines the collision theory of the reactions. For a collision to be effective, a particle must have minimum activation energy and a correct alignment. The number of the collisions per second per unit volume of a reaction is called collision frequency, that is capital Z. The Arrhenius equation can be written as K is equals to ZAB exponent raised to power minus EA by RT. According to collision theory, another factor capital P called steric factor, which refers to the orientation of the molecules which colloid, is important and it contributes to the effective collisions, thus modifying the Arrhenius equation as K is equals to P ZAB exponent raised to power minus EA by RT. So, dear children, in this module we have studied about the Arrhenius equation and the effect of temperature on the rate of reaction, the impact of the catalyst and the collision which has to be with the proper energy and the proper orientation. I hope all the things which we have learned is clear to you. Thank you.